Hello everyone, this is our first lecture video for P3 Chapter 10 Complex Number. Currently on the screen is the lecture notes for Chapter 10, page 1. Right, first of all, introduction to complex numbers. So before we go through the points on page number 1, let's recap some of the knowledge we have learned before during our very first lecture on in semester 1. Okay. So recall that during our very first lesson in semester 1, you were introduced to number system. You were introduced to number system in mathematics. Okay. So you were introduced that the set of natural numbers is denoted by this capital letter N with a double vertical line. Some people write it this way. This is the set that contains all the positive integers starting from 1, 2, 3, and so on. This is an infinite set because it contains an infinite number of elements. And then you will also introduced to the set of integers. The set of all integers. The symbol is the capital letter Z with a double slanted line, and this set of integer would include negative integers, 0, and also positive integers. So the way we usually write this is we write 3 dots followed by -3, -2, -1, 0, 1, 2, 3, and 3 dots at the back. So this is again an infinite set containing an infinite number of elements. And we notice that all the positive integers are contained in this set of Z. But all the positive integers are also elements in the set N. And so from here, we can see that the set of natural number is a subset of the set of integers. So we have this subset relationship here between N and Z. If we were to depict this information using a Venn diagram, then we can draw the set of natural number inside. It is contained within the set of integers Z. So for example, you have your elements 1, 4 inside the set N, and you have your 0, -1, and -4 outside the set N, but within Z. Okay. Okay. Then we will also introduce to set of rational numbers. A set of natural numbers, the standard symbol is Q with a vertical line at the side. Then it contains all numbers that can be written in the form of P over Q. It is the set of all numbers in the form P over Q such that P and Q are both integers. And also your denominator Q cannot be 0. As examples of natural numbers, examples of rational numbers. Examples of rational numbers. You can have 1/2, you can have -3 over 4, you can have 5 over 2. Improper fractions are also rational numbers. In fact, any decimal number that terminates, for example, the number 1.23, because it can be written as 123 divided by 100, and so it still falls under the set of rational numbers. Okay. Of course, all your integers are also rational numbers. For example, the integer number 3 can be written as 3 over 1, therefore it is a rational number. -4 can be written as -4 divided by 1, therefore it is also a rational number. Okay. Since all integers are rational number, we observe that the set Z is contained in the set Q. Z is a subset of Q. And earlier we also know that the set N is contained in Z. And so now we have a multi-layered subset relationship. And N is a subset of Z, Z is a subset of Q. Then we also realize that there are certain real numbers that cannot be written as a fraction where the top and bottom are both integers. For example, the number pi, which is 3.141 something. So this number is not rational. square root of 2, for example, you have 1.4142 and so on. This decimal value is not terminating. It is not terminating. And it is also not recurring. And so a decimal value that is not terminating and not recurring is not a rational number. And we learned this before in chapter 0 very early in the semester. So this is also not rational. And so mathematicians have decided to introduce a name known as real number to contain all the rational number and all the irrational numbers. Pi and Z2, they are not rational. They are also known as irrational numbers. And so a set that contains all rational numbers and all irrational numbers is known as a set of real numbers. Set of real numbers R. So this set would include all rational numbers and all irrational numbers. Okay. Because the set Q, the set of all rational number, is contained in the set of real numbers, right now we have a subset relationship involving 4 sets now. Right? We have N contained in Z, Z contained in Q, Q contained in R. Okay. Okay, now let's read the notes on page 1 of chapter 10. Okay. So first of all, introduction to imaginary numbers. And so imaginary number is a number that is not real. It's not within the set of real number. And so first of all, why do people come up with this idea of imaginary numbers? Okay. So let's read through point number 1 and 2. Okay, within the real number system, the quadratic equation ax squared plus bx plus c equals 0, where the coefficient of x squared, which is a, is not 0, and where a, b, c are real number coefficients. This quadratic equation will have real roots if the discriminant b squared minus 4ac is more than or equal to 0. This is something that we have learned before in P1 quadratics. And then in P1 quadratics, we also know that if b squared minus 4ac is strictly less than 0, then that equation would have no real root. Point number 2 gives us one such equation that has no real root. X squared plus 1 equals 0 has no real root. To verify this, x squared plus 1 equals to 0. This equation has the value of a being 1, b being 0, and c being positive 1. So its discriminant b squared minus 4ac is 0 squared minus 4 times 1 times 1. You get a negative 4, which is less than 0. Therefore, the quadratic equation has no real root. Right, so we usually say such equation has no real roots, and in our P1 syllabus, it will just stop there. We won't proceed further to solve for x. We just say that it has no real roots. But now, in P3 chapter 10, we will learn how to proceed further when you have such a quadratic equation with no real roots. Point number 2, second line, it says, there is no real value of x such that x squared is equal to negative 1. When you move the plus 1 over to the other side, you have x squared equals to negative 1, and we know that for any real number x, x squared must be x squared must be greater than or equal to 0. So since the left-hand side of the equation is always non-negative, but our right-hand side is obviously negative, that means equality will never happen. And that also means there is no real solution for this equation, x squared equals negative 1. Okay. Now, in this case, mathematicians have decided to introduce a number I. This I is a standard symbol. This I is a standard symbol known as the imaginary unit. So this I is defined by I squared equal to negative 1, or square root of 1 equals to I. Square root of minus 1 equals to I. Yeah, square root of minus 1 equals to I is the definition that we will be using in our syllabus for the symbol I. So if cert of -1 is equal to I, when you square both sides, then you have cert of -1 squared will be equal to I squared. And we know cert of -1 when we square, I mean when you have a square root and you have a square at the outside, the square and the square will cancel, giving you a -1. Right, so these are two things that you have to remember for this chapter. Okay? Cert of -1 is equal to I, and also I squared can be written as -1. And later, when we do calculations, whenever we see I squared, we will always replace it by -1 to simplify things. Right, so two things to memorize here. Cert of -1 is equal to I squared is equal to -1. Okay. Okay, now, if we introduce such a number I, then the equation x squared equals to -1, the right-hand side of -1 can be now replaced by I squared, because we have I squared equal to -1. And then, when this square goes over to the other side, we will introduce plus minus square root I squared as usual. We'll introduce plus minus square root as usual, and so we end up with x equals to plus minus I. Yeah, so that's how we get the two roots for the equation x squared plus 1 equal to 0. And so these two roots, plus I and minus I, they are not real root, but they are complex root. Okay. So okay, this plus I and minus I, they are known as imaginary number, and I is also known as the unit imaginary number. And some books call it the imaginary unit. It is the simplest unit for imaginary number. Right, then now we will move to point number 3. Imaginary number is a square root of a negative number. Okay, for example, square root of -4. So in this chapter, we might encounter square root of a negative number, and we are expected to simplify it and write it in terms of I. So square root of -4 should be interpreted this way. We will factor out a -1, so writing -4 as -1 times 4. And then we'll apply the property that the square root can be distributed over multiplication. Okay, so that cert of -1 times 4 can be written as cert of -1 times cert of 4. But cert of -1 by definition will be written as I. Cert of 4, this is just cert of a positive number. We will simplify it to become 2. So you end up having 2i, as printed there. Okay, the number 2i is an imaginary number because of the presence of I. And so any number, I mean, I multiplied by some real coefficient is known as an imaginary number because the I is present there. Okay. So there's this one question here, express negative of square root -4 in terms of I. Okay. Now, the thing to be careful of is there's nothing we can do about the negative inside here. I mean, you cannot combine this negative with the negative at the outside. Okay, the two blue colored negative do not cancel each other. Okay, they do not cancel each other. We cannot pull this to the outside. Okay, we cannot do that. Right, so the negative at the outside, it should be left alone. Okay, we are not going to touch this negative at the outside. It can't be combined with the negative at the inside of the root. Okay, so if we are asked to simplify this number, then what do we do? Okay, the negative at the outside will leave it alone as mentioned just now. The -4 at the inside, it will be interpreted as -1 times with 4. Okay, then square root can be distributed over multiplication. So I have cert of -1 times with cert of 4. The negative at the very front is still there. Square root of -1. By definition of I, it is now replaced by I. While the square root of 4 will be simplified to become 2. So we end up having -2i. And so -2i will be the most simplified form. Okay, so notice that throughout the entire working, this pink colored negative that is outside the square root remain untouched. It remains untouched. Now there is one note at the very bottom there. It says that the rule square root of AB equals to square root A square root B cannot be applied if both A and B are negative. And so this is something we have to be careful of. Okay. But square root of a product, we usually say that like if we have surd of 15, which we can write as surd of 3 times 5, it can be safely written as surd 3 times surd 5. And this is a correct result. But however, the distributive property of square root over multiplication, it cannot be applied if both the numbers involved in the multiplication are negative. If both A and B are negative, then we cannot apply the distributive property of square root over product. Okay. If one of those A and B, if exactly one of A and B is negative, it is still okay. For example, square root of negative 4 is interpreted as square root of minus 1 times 4. Then you get surd of minus 1 times surd of 4. You get I times 2, end up having 2i. This is still correct. When you have one term in the product being negative, the other is positive, it is still okay to distribute your square root over the product. However, if both of them are negative, if both of the numbers involved in the product is negative, then we cannot distribute. Now, to convince you why we can't do that, I will show you one example. Okay. For example, square root of 1. Okay. Square root of 1, when there's nothing in front of the square root, it is understood to be having an invisible plus at the front. Right? So square root of 1 means the positive square root of the number 1, and we know the answer must be 1. Okay? This is the only answer. This is the only answer. Is 1. And there shouldn't be a second answer. No. Okay. The same square root of 1. Okay, I can write my number 1 as negative 1 times negative 1. Okay, the number 1 can be written as minus 1 times minus 1. Up to this step, it is still correct. It is still correct up to this step. Now, if I proceed to distribute my square root over the product so that I have surd of minus 1 times surd of minus 1, and this becomes wrong now. This becomes wrong because in the product form minus 1 times minus 1, if both the components involved in this product form are negative, and negative 1 is negative, negative 1 is again negative, we have both negative. And when both are negative, the square root cannot be distributed over the product. And now, just to convince you why this is wrong, I will just continue my working, and you will end up getting a contradicting result. Surd of minus 1 is I. Surd of minus 1 is I. The second surd of minus 1 is another I. So we can write as I times I. I times I is I squared. But I squared, by definition, you can refer back to point number 2. By definition, I squared is negative 1. But this negative 1 is different from the correct answer of 1. We know that square root of 1 must be 1. It is the only answer. Now we get a different answer. We have the same question to begin with. The question is surd of 1. But you end up getting a different answer. This is not 1, therefore wrong. Therefore, it is wrong. And this thing is wrong because we made a mistake in the middle. The step where we distributed the square root over the product of minus 1 times minus 1, this is where the mistake happened. So this is where the mistake happened. Mistake happened here. The step where we distributed square root over the negative 1 times negative 1, and that is where the mistake happened. The square root of 1 must be 1. It cannot be negative 1. We know for sure there's only one answer. Okay. And so just remember, when you have square root of a product, we cannot distribute the square root over the product if both the components in the product are negative. If both are positive, of course, we can distribute. If one is negative, another is positive, we can also distribute. It is only for the case when both A and B are negative that we cannot distribute the square root. Okay. Now let's move to the next point. Okay, so earlier we have learned about imaginary number, and so any number that contains I, it can be I alone or it can be some coefficient times I. It's known as an imaginary number. Okay. Now, let's learn about complex number. A complex number is defined as a number of the form x plus iy. Sometimes we will write as x plus yi, it doesn't matter. Iy and yi are the same, where x and y are real numbers. Okay, so an example of complex number is 3 plus 4i, where 3 and 4 are both real number. So this is a complex number. 3 plus 4i, the whole thing is a complex number. So, according to this definition of complex number, it simply says that any number that can be written of the form x plus yi, where x and y are real numbers, is known as a complex number. And so it doesn't say that x and y must be non-zero. In other words, it allows x and y to be zero. You can have x is zero, you can have y is zero, you can also have both x and y is zero. It still satisfies the definition of the complex number. Okay, point number 5 says a complex number is often denoted by the letter z. So it's common for people to write z equals x plus yi. The real number x, the part that doesn't contain I, this x here that doesn't contain I, is called the real part of the complex number z. In symbolic form, we write re bracket z is equals to x. So for example, if we are given that z is equal to 3 plus 4i, and then the real part of z, written re bracket z, it is the real part of the number 3 plus 4i, and it is simply 3. But the real part of 3 plus 4i is simply that number that doesn't contain any I. We'll just take it. So you should be familiar with such notation, re bracket z. Some books may write re followed by a space z. This is an alternative notation that is also acceptable. So imaginary part of z is the real number y, which is the coefficient of I. So imaginary part of z is the coefficient of I in the complex number z. So using back the same example, the imaginary part of z you can write as im with a space z. Some books write as im bracket z. It is the imaginary part of 3 plus 4i, and it is simply the coefficient of I. It's simply the coefficient of I, which is the number 4. Okay, notice that when we take the imaginary part of z, we are only taking the coefficient of I. We do not take the I itself. We only take coefficient of I. We do not write 4i here. We only take the 4. We don't take the I. We only take coefficient of I as the imaginary part. Next, consider this complex number z equals x plus yi, where x and y are both real values. So it says if y is equal to 0. So moments ago I mentioned that in the definition of complex number, it just requires that number to be able to be written as the form x plus yi, where x and y are real. It doesn't say that x and y must both be non-zero. And so, in other words, it allows x to be 0 or y to be 0 or even x and y to be both 0. So, what happens if y happen to be 0? If y happen to be 0, the complex number is purely a real number. or purely real. Sometimes we simply use a single word real, or simply we use a single word real is understood as purely real. So for example, um, z equals to 3 plus 0i. And so in this case, your x is 3, your y is 0. X is 3, y is 0. And 3 plus 0i, of course, can be written as 3. Because 0i is simply 0 and 3 plus 0 is just 3. Now, this is a purely real number. Because it doesn't have any imaginary term. It doesn't contain I. It doesn't contain I. That's why we say it's purely real, because it doesn't have any imaginary term. Okay. Next, part B says if x is equal to 0, for example, if your complex number z is given as 0 plus 4i, where the x is 0 and the y is 4. Okay, so for the case when your x is 0, 0 plus 4i can of course be written as just a single term 4i. And so this term is purely imaginary because it only has the term that contains I. It doesn't have a separate term without I. So this is known as a purely imaginary number. And recall that I is an imaginary unit. And so some number times I is a purely imaginary number. Because it doesn't have a separate term without I. So 4i is known as a purely imaginary number. So we say it is purely an imaginary number or simply purely imaginary. So when describing purely imaginary number, it is common for people to include the word purely. But when describing a purely real number, it is common for people to omit the word purely. And this is just some common practice. When the question says a number is real, it's understood as purely real. But part C says a complex number x plus iy equals to 0. So x plus iy is equal to 0 if and only if both x and y are 0. So part C is trying to tell us that if x plus yi equals to 0, the 0 on the right, it should be interpreted as 0 plus 0i. It should be interpreted as 0 plus 0i. And then upon comparing both sides, later on page 7, we will learn about equality of complex numbers, and it's actually that property that allows us to compare the two sides when we have two equal complex numbers being equated. Okay, but anyway, here it says if your right hand side happen to be 0, that 0 can be interpreted as 0 plus 0i, because obviously 0 plus 0i is just 0 plus 0, and of course that would be 0, right? So we can compare both sides, and we can then say x is equal to 0, and the coefficient of I on both sides can also be equated, y equals to 0. Yeah, and so this is simply to tell us that this 0 here, it should be interpreted as 0 plus 0i, okay? So that you can easily figure out what the values of x and y should be. And so later on in this chapter, sometimes if you get some complex number equation, something like p minus 3 plus with q minus 4 I equals to 0, and then you can interpret the right hand side as 0 plus 0i. Upon comparing both sides, you have p minus 3 equals 0 and q minus 4 equals 0, and then you can solve for p and q. So we'll do more on this on page 7 later in this chapter. Okay. Now point number 7. Generally, unless otherwise specified, a complex number x plus I times 0, or simply x plus 0i, it will be written as x only. And so it's common for people to write x plus 0i as simply x. For example, 4 plus 0i will be written as 4 only. We usually do not write out the 0i. And 0 plus iy is commonly written as iy only. For example, 0 plus 3i will be written as just 3i. Okay. Point number 8. Point number 8 says, obviously, any real number can be written in the form x plus I times 0, where x is a real number. So, for example, 3 is a real number. Hey, we all know 3 is a real number because 3 is an integer, and integer, the set of all integers is a subset of the set of real numbers. And so an integer must be a real number. Hey, but 3 can be interpreted as 3 plus 0i, where both 3 and 0 are real number. In other words, you can treat your x as 3 and y as 0. So we have already written the number 3 in the form x plus yi, where x and y are both real numbers. It already satisfies the uh, definition of a complex number. So we can say this 3 is not only a real number, but it is also a complex number. It is a complex number. And so this is the handwritten form of the set C. The set C is used to denote the set of complex number. The set of complex number is denoted by the set C. You usually write a vertical line near the side. So this is the handwritten form of the set C, denoting the set of complex numbers. But all real numbers are complex numbers because any real number can be written as the real number itself plus with 0i. And so all real numbers must be complex numbers. And so now this adds on to the multi-layered subset relationship that I mentioned at the beginning of this lecture. And so we know that natural numbers are contained in a set of integers. Set of integers is contained in a set of rational number. Rational number is contained in the set of real number, and real number is contained in the set of complex number. So now we have this uh, multi-layered subset relationship, and this is the newest addition to it. So if you depict this on a Venn diagram, you have n being at the innermost, followed by z at the outside of it, followed by the set q, then followed by the set of real numbers, and also the set of complex number. So the set of complex number, or the set C, it will be the largest number system that we will learn in our syllabus. We will not learn anything larger than C. Okay. So just to give you some examples in every set. So natural numbers include numbers like 1, 2, 3, 4, 5, and so on. So I have 1, I can have 4 here. So the set Z, it would include 0 as well as negative integers, -1, -4, and so on. Okay, the set Q, the set of all rational number, it of course includes all the integers. The 0, -1, -4, 1, and 4, they're all in Q. Then some numbers which are outside Z but inside Q, it will be number like 1/2. It will be a terminating decimal, for example, 0.61. It can also be recurring decimal, 0.16666, and so on. You can also have like 5/3 and improper fraction. And they are all also under the set Q. You can also have negative fractions, -3/4. Okay, real number. Real number will include all the rational numbers and irrational numbers. Irrational numbers, some examples are pi, you can have square root of 2, you can have a cube root of 7, and many more. Okay. Now, the set of complex number, or the set C, some elements which are in C and not in R, it will be the number I itself. You can have like 3 plus 4i, you can have minus square root 2 plus square root 3i. So basically anything that contains I, it will be in the set C but not in the set R. Okay, so notice that this set C, it contains everything in R. And so any number that is real, for example, if I pick this half here, this half must be also a complex number. This half must be also a complex number because the number half can be written as half plus 0i, where both half and 0 are real numbers. So it already satisfies the definition of a complex number. So any number that is of the form x plus yi, where x, y are real numbers, this is a complex number. So all real numbers must be complex numbers, but a complex number is not necessarily a real number. Okay. Now, going back to point number 8, the note at the bottom of point number 8 says, a complex number in general cannot be represented as a point on the real number line. Hence, complex numbers do not obey the rules on order. And so what do I mean by the rules on order here? That means that it is impossible for us to make comparison between two complex numbers and say that one number is larger than the other. So in other words, it makes no sense. It makes no sense to write inequalities involving complex numbers. Okay, recall that in the real number, when we consider real number, it is always possible to compare between two real numbers and say that one number is larger than the other. For example, if you want to compare the number 3 with 4, we know 4 is on the right of 3, so we say 4 is greater than 3. Or in other words, 3 is less than 4. Because we can always visualize each real number as a point on the number line, and the one that's on the right must be the larger one. Another example, you can compare between -1 and negative 4.5. Right? So since negative 4.5 is on the left, we say minus 4.5 is less than -1. Right? So yeah, so being able to visualize the number as a point on the number line enables us to tell which number is larger when we talk about real numbers. However, for complex number, for example, the number 3 plus 4i, this number, it cannot be represented on a number line. It cannot be represented on a number line. Any number that contains I, it cannot be represented on a number line. So if we want to compare 3 plus 4i and 5 plus 2i, hey, between these two numbers, which one is larger? Well, we cannot compare at all. But even if I set the coefficient of I to be larger, for example, 3 plus 4i I compare with 6 plus 8i. Can I compare and say 6 plus 8i is larger than 3 plus 4i? No, we can't do that. We can't do that. We cannot compare between two complex numbers that contain I. Because any number that contains I cannot be represented on a number line. So that makes it impossible for us to make comparison. So going back to the notes, it says, if you have two complex numbers z1 and z2, z1 less than z2, writing an inequality involving two complex numbers is meaningless. It is meaningless because when a number contains I, it makes no sense to make comparison between them and claim that one is larger than the other. We cannot make comparisons for numbers that contain I. And so inequality will only make sense if the two sides of the inequality are both real numbers. If you have something that contains I, you cannot write inequality involving it. So 3 less than 6, this is perfectly fine. But 3 plus 4i less than 6 plus 8i, this makes no sense. So please do not write any inequality involving I. It makes no sense. Okay, now let's move on to the next page. We'll do exercise 1. Okay, so this is just a very quick warm-up for us to simplify complex numbers. And write down each of the following complex numbers in the form a plus ib. It simply means a plus bi, where a and b are real numbers. Okay. So recall that there are two things that we need to remember regarding I. First of all, surd of -1 is equal to I, and if we square both sides, we will have -1 equals I squared. So we have to remember these two things in the process of simplifying such numbers. Now let's do part A. So they tell us x is a real number, and so x can be treated as just some number without I plus surd of -1. Okay. So surd of -1 by definition, it is I. So it simply becomes x plus I, and we are done. We are done. It already has the form a plus bi, where the a is x and the b is 1. There's an invisible 1 in front of the I. So the b is 1. So here the a is x and b is 1. X is real, 1 is real, so we are done. Now moving on to part B. 3 minus surd of -9. First of all, a reminder again that we cannot combine these two negative here. These two negative cannot be combined to become a single class because the negative at the inside of the surd, we cannot pull it out. We cannot pull it out. So what we can do is just to first write -9 as 9 times -1, or -1 times 9. Then we can distribute the square root over the product. So this can be written as surd of 9 times surd of -1. But it's okay to do such distribution because 9 and -1, they are not both negative. If only exactly one of the two components is negative, we can still distribute the square root. So it's fine. Square root of 9 becomes a 3. Surd of -1 by definition becomes an I. And that's the answer. So we already have the form a plus bi, where a is 3 and b is -3. Next, moving on to part C. -2 plus square root of -3. -2 plus, so this one I write as 3 times -1. So distribute my square root over the product. Set 3 remains unchanged. There's no way for me to simplify set 3 any further. And also because this is pure maths, try not to convert the decimals unnecessarily. In pure maths, we always prefer to keep the number in exact form wherever possible. We'll avoid converting the decimals in pure maths whenever we can. So surd of -1 is I, and that's it, done. Okay, there's a remark at the bottom of part E. It says surd of -1 times surd 3 is usually written as I surd 3 rather than surd 3i. This is to avoid confusion with surd 3i, where the I is contained in the square root. Okay, so notice that the printed answer there is actually the same as my answer here. It just writes the I in front of the surd 3. It means the same thing. Okay, so it is perfectly fine to write it this way. It is actually okay to write like this. For some people, they just prefer to write the I in front to avoid confusion. Like they prefer to write I in front of the surd 3. And some people prefer to write this way. But it's not a must to write the I in front. It is perfectly fine to write the I at the back, as long as it is very clear that your I is not contained in the square root. This set3 I is not the same as set3 times I. It's not the same. And so if your I is not contained in the square root, it just make sure that when you write it, it is very clear that the I is not contained in the set3. Like, you can leave a bit of space in between the set3 and I. Just leave some space in between. Don't write your I too near the set3. If you write it this way, then it's a bit risky for it to be misinterpreted. So if you write set3 followed by I, then make sure that your I is written at a bit of distance away from the set3 to avoid misinterpretation. Okay. Right. Then next, for part D. P plus square root of minus q squared, where P and Q are both real numbers and Q is positive. Right, so nothing to do with the P there, so we just copy back the P. Square root of minus q squared, it will be interpreted as -1 times with q squared. The q squared must be positive because of the power 2 and because q itself is also positive. And so q squared must be positive. So -1 is negative, q squared is positive. It is okay to distribute my square root over the product because not both the components are negative. Surd minus 1 times surd of q squared. Surd minus 1 by definition should become I. Surd of q squared. Instead of q squared, let me make a remark here. Surd of q squared, it would usually become modulus of q. When we have, for example, like in chapter 1, in chapter 0, in semester 1, there's one section on square roots, which says if you have square root of a real number squared, where the square is inside the square root, it should be simplified to become modulus of q. But because q itself is told to be positive, modulus of q must be q itself, because we know that q is positive. So yeah, it is due to q being positive that allows us to simplify surd of q squared to become just a simple q. If we did not know that q is positive, then we actually need a modulus around the q. And so just be aware of this. If you have forgotten, please revise back chapter 0, which we did during semester 1. Okay. So you have P plus QI and that. The last one is part E. K plus with square root of K squared minus 3K squared. And they tell us that K is real, K is positive. So recall that if you have square root of A minus B is not the same as surd A minus surd B. We cannot simply distribute square root over a minus. Square root cannot be distributed over plus or minus. Right? So we cannot simply distribute our surd that way. Right? But here notice that k squared minus 3k squared can be simplified. Right? Because k squared has an invisible 1 in front. Right? It's simply 1k squared minus 3k squared, so we can compute the coefficients 1 minus 3. Okay, so let's do that first. Negative 2k squared upon simplifying. And then this will be interpreted as negative 1 times 2 times k squared. Right, then this square root can be distributed over the product. Now, it's actually safe to distribute this square root over the product, because if you treat this as -1 times surd of 2k, sorry, if you treat this as -1 times 2k squared, the 2k squared is actually positive, -1 is negative. Because not both are negative, we can safely distribute it. So let me do it a bit slower this time. This is surd of -1 times surd of 2 times k squared. And then this part is again safe to distribute my square root over the 2 and k squared, because both 2 and k squared must be positive. In the presence of power 2 guarantees that k squared must be positive. And so I have k plus surd of -1 by definition must be I. This is surd of 2, and this is surd of k squared. Because k is itself positive, it usually surd of k squared should be simplified as modulus of k, but because k is itself positive, it allows us to simplify to become just a k without modulus, because k is positive. So now we have k plus I times surd 2 times k. And then just make it nicer, k plus I k surd 2. Okay, done. Okay, of course, if you prefer to write your I at the back, like if you prefer to write k plus k surd 2 with an I at the back, of course, this is also fine. If you prefer to write your I at the back, make sure that your I is written at a bit of distance away from the surd 2, so that it's clear that your I is not contained in the square root. Okay. Yeah, so this is question 1 done, and now we'll move to question 2. Write down the real part and the imaginary part of each of the following complex numbers. This is also a very quick warm-up. And recall that the real part, it is simply the term that doesn't contain I. Imaginary part is the coefficient of I in the complex number. Okay, so, well, the answers are all printed out already. So we'll just read through the answers, right? So Z1 is this complex number written as A plus IB. So the real part will be A. Okay, when we write real part, we'll write RE bracket Z1. So RE bracket Z1 simply means the real part of the complex number Z1. So it's just A. Imaginary part of Z1 is B. B is a coefficient of I there. For part B, a real part of Z2 is a number 2, while the imaginary part of Z2 is negative Z3. And so just take note that 2 minus I Z3 is actually 2 plus with minus Z3 times I. Right, so the coefficient of I is actually negative Z3. And you have to include the negative. You have to include the negative. And because the coefficient of I is negative Z3. You have to include the negative there. Okay, so for part C, real part is -1/3, imaginary part is 2/3. This one is obvious. And for part D, pi is a term that doesn't contain I, so that is a real part. So the real part of Z4 is pi, and the imaginary part of Z4 is surd of 7. And so it is okay for the real part and imaginary part to be irrational numbers. Pi is irrational. There's nothing wrong to have the real part being irrational, and surd of 7 is also irrational. It's perfectly fine. As long as a complex number can be written as x plus yi, where x and y are both real, then it is a valid complex number. And recall that real number includes rationals and irrationals. So it is okay for your x or y or both x and y to be irrational. It's perfectly fine. So there's nothing wrong having a pi here as the real part. Although pi is irrational, there's nothing wrong. Okay. Okay, I'll stop the video here. I'll continue with the next video. I'll continue in the next video.